In the future, I'll focus on the iron neckties. So let's take a look at the multi-band model for neckties. The Fermi surface structure is more complicated in the neckties. There are 4 visible Fermi sheets in the 3-dimensional brilliant zone, 2 Hall sheets around gamma and 2 electron sheets around pi 0 and 0 pi. You can see the structure is quite 2-dimensional, so we can project it on a 2-dimensional plane. These 4 bands are the basis of a 4-band model. In some models, people assume the coupling between the 2 hole pockets or between the 2 electron pockets is weak, so we can reduce the 4-band into an effective 2-band model. The energy dispersion for the normal state looks like this. Epsilon alpha describes the whole band. Usually, it is quite circular. The electron band is not quite circular, so we can adjust the ratio of the effective mass of the X component and Y component to get the elliptic pockets. Theoretical results show that the different ellipticity can affect the results quite profoundly. The spin density wave Hamiltonian contains the density-density interaction and umklapp pairing hopping terms. If we consider all the inter- and intra-band interaction, the Hamiltonian will look like this. The spin density wave Hamiltonian will look like this. One example of the multi-band model is from Ehrman and Chubko's paper. They use the 3-band model to explain the metallic property in the iron necktie parent compound. The 3 bands are 2 electron pockets and 1 hole pocket. Here we only consider the density-density interaction and the hopping pair interactions between electron and hole pockets. And also assume the pockets to be circular. Define the order parameter sets delta Z1 and delta Z2. One is the order along 0 pi and the other is along pi 0. We can use it to decouple the interaction terms. They diagonalize the matrix, and then we can diagonalize the matrix and get the new energy dispersions for the new quasi-particles. The conclusion of this result is that the spin density waves stay metallic because one of the new bands is not gapped. It remains as the same as the bare electron energy dispersion. And also I will have to include the superconductivity in the system if I want to study the coexistence state. The gap symmetry in neckties is different from other materials. There are these 3 possibilities that most people agree on. Because the night shifts show that superconducting spin symmetry is singlet. So we may have S-wave symmetry or D-wave symmetry. The different gap symmetries may influence the behavior of the physical observables, such as temperature dependence of penetration depth. So we we can include these symmetries in the calculation and compare with experiment data to find out what the symmetry is in the materials. In the future, I will use the same techniques to study the ionic ties. The same techniques for multi-band model to study the ionic tie system. There are some assumptions which could be generalized, such as including more bands, including interband interaction and interband interaction, and including the ellipticity of the electron pockets. Also, some people argue that the spin density wave may have a K dependence, which means the spin density wave order parameter is not a constant on the Fermi surface. However, this is not generical. This is not universal. The orbital contribution may be important even though some of the orbital bands are not shown on the Fermi surfaces. The effects of disorder and impurities is important for the real-world experiments. So I would like to explore these things in the future. Thank you.